In 1915, Einstein published his general theory of relativity. Soon after, physicists realized that his theory allowed for catastrophic gravitational collapse in places in space with extreme density, places like the core of a colossal dead star. In these places, the mass and energy would fall in on itself, pulling space and time with it, creating a sort of hole in the universe, from which nothing could escape. Not any particle, not even electromagnetic radiation or light, the fastest thing in the universe. These are called black holes, and for a time we believed this was how the universe would end. Just a bunch of these black holes, having gobbled up all the mass and energy in the universe, floating around indefinitely. That was until 1974, when Stephen Hawking published a paper titled Black Hole Explosions and a follow-up paper in 1975, where he attempted a messy union of quantum mechanics and general relativity. He focused specifically on the quantum fields and how the gravitational field of a black hole would affect them. He knew that the intense gravitational field would have an effect, but what? First, what are these quantum fields? Quick explanation. Quantum fields permeate all of space-time, everywhere and anywhere, your house, a galaxy, and the device you're watching this on right now. Particles in these fields, like electrons or muons, can be represented as waveforms. Just like a note on a string, these waveforms or particles have underlying modes. These modes exist even in the absence of these particles, and due to quantum uncertainty, these modes fluctuate. These fluctuations can be strong enough that they are thought of as virtual particles, popping into existence for an extremely short amount of time, based on the uncertainty principle. Hawking did a bunch of math around the gravitational fields and found something fascinating. The energy from the black hole's gravitational field can give one of these virtual particles sufficient energy to pair produce, or turn into two particles, each traveling in opposite directions. One of these particles escapes and the other one of them falls into the black hole. The particle that escapes carries some of that energy that gave it existence that came from the black hole's gravitational field with it, decreasing the energy and therefore mass of the black hole. This is Hawking radiation, and to a faraway observer, Hawking found that these particles escaping from the black hole appear as thermal radiation. His calculations show that the smaller the black hole gets, the hotter it appears, eventually becoming incredibly hot and exploding in a giant mass of different particles. Math and science are tools we use to describe and interpret reality. This interpretation of Hawking's math is one of a few, and there's no single scientific consensus on which is the most accurate. Only with further scientific observation will we truly know what is really going on around black holes. Thanks for watching.